So one of the most important factors when it comes to ranking acidity is looking at the number of resonance forms or the important resonance forms in a molecule. And one of the best ways to describe this is by looking at vitamin C. Vitamin C has multiple acidic hydrogens, and we want to see which of these hydrogens is actually the most acidic by the number of resonance forms that it provides. So we have three different hydrogens over here that I'm going to compare today. And just a quick review on resonance, it's the movement of electrons between atoms. And over here, you don't have one electron configuration or the other, but rather it's a hybrid and it's constantly interchanging. And so let's consider the first case scenario where the acidic hydrogen is on this bottom left over here. When we get rid of that hydrogen, we get this atom right here, where we have a negative charge on our oxygen atom. Now this negative charge can move because of resonance. It can actually move over here and become a pi bond with this carbon. Now this carbon then will end up having 5 bonds. We'll have 3 sigma and 2 pi, and that's not possible. So what ends up happening is that this pi bond over here that I had with the other carbon will move and become a lone pair on that carbon. And so over here we remove this, we add that bond that we generated and a negative charge over here on this carbon. Now this carbon can also move that negative charge around, and it can move it to be bonded with the carbon that's right next to it that has a pi bond with our oxygen. Now since that carbon will end up having 5 bonds, it will actually move its pi bond with oxygen to become a lone pair on oxygen. And we end up getting this. So over here we delete this. We end up having a negative charge on oxygen, and this new bonds over here. And our old oxygen still has 1 pi bond on it. And so this is our new configuration. And this constantly interchanges. This constantly goes back over here, and this goes back over there. And it keeps moving in between the atoms. And so we denote it as this by writing interchanging arrows in between, and we have brackets around all of them. And since the whole molecule has a negative charge, we just put a negative charge out there. So this acidic hydrogen over here has 3 resonance forms. Now compare it with this hydrogen over here. When we get rid of it, we get this atom right here, where we have a negative charge on this oxygen. And this negative charge can move and form a pi bond with carbon. And this carbon, not trying to have 5 bonds to not break the octet rule, will move its pi bond with the other carbon back to that carbon and become a lone pair there. And so we get this, where we have a pi bond with oxygen and a negative charge or a lone pair on this carbon right here. And so that's it. That's all that carbon can move, really. It can't really move its resonance anymore else because there's no atom next to it that's sp2. All the other atoms around here are sp3. And so we put the brackets over here, say that we only have 2 resonance forms. We put a negative charge outside because this molecule, the vitamin C, has a negative charge on it. And then we'll compare it with this last hydrogen over here. When we get rid of that hydrogen, what ends up happening is that we just have a negative charge on this oxygen. And look, there's no sp2 atoms around it, and so we can't move that negative charge anywhere, and so it's stuck. So there is no resonance forms. There's 0 resonance forms. And so over here, when we compare them, look, there's only 1 form. Over here we have 2 forms, and over here we have 3 possible forms. And so when we're comparing these in acidity, the one with the most amount of resonance forms is the most acidic. So this is number 1 because it has 3 resonance forms. And over here, this is number 2 in terms of acidity because it has 2 resonance forms. And this is the least most acidic among those 3 because it has 0 resonance forms. And so that is how resonance affects the acidity of a molecule.